So by this point we've made it all the way through the Precambrian and we're now into the Phanerozoic. So if you remember, the Paleozoic is one of the three constituent eons of the Phanerozoic, the other two being the Mesozoic and the Cenozoic. So by the end of the Precambrian we've managed to form a substantial portion of most of the continents, with the exception of Europe and Asia. A lot of the build-up of those two continents occurred a little bit later. Also in the Precambrian we've had our first three supercontinents, so that's Nuna, Rodinia and Panatia. So the breakup of Panatia and a sudden rapid increase in plant and animal fossils marks the start of the Cambrian. So we can see these changes as we transition from the Precambrian into the Cambrian. We can see a sudden increase in the amount of passive continental margins. So that, if you remember, those are the nice, safe, boring marine environments in which life loves to live. And if we look in the rock record, we can suddenly see that the abundance of fossils increases massively as we go into the Cambrian, because the Cambrian is marked by the appearance of large numbers of macroscopic organisms, or organisms that you can just see with the naked eye. And a lot of those organisms will have hard shells or skeletons, in which case they are far more likely to fossilize successfully. So we'll see these animals appearing in the rock record in the form of fossils a lot more commonly than the more soft-bodied organisms we had right at the end of the Precambrian. So during the early Paleozoic we have sediments being deposited on cratons, producing two distinct types of environment. We have the platforms, so that's areas of Precambrian crust which get covered by younger sediments, and we have areas which we refer to as shields. Those are areas of Precambrian crust that are exposed, so you can actually go and physically touch the rocks, you can walk on it. So the rocks deposited onto the cratons during the Paleozoic consist of a mixture of detrital, so that's clastic, and chemical sedimentary deposits which have been deposited into shallow seas underlain by continental crust. So the term for one of these shallow bodies of seawater which is on top of continental crust is called an Epeiric sea. Of course they're different to larger ocean basins where of course the water is sitting on top of oceanic crust. So during the Paleozoic and the Mesozoic, these seas transgressed and regressed due to periods of continental glaciation and or plate tectonic movement. So we're going to see large-scale global transgressions and regressions associated with either glaciations or, in one or two instances, actual large-scale tectonic processes. So sediments within these seas were deposited as horizontal layers, as most layers of sediments are, so they formed these nice sheets. So they were laterally extensive but quite thin. However, tectonic pressure could lead to the formation of gentle regional folds, which are essentially produce things which we refer to as arches, domes and basins. So obviously an arch essentially is just like a large fold. A dome obviously would be a three-dimensional fold, and a basin would obviously be a three-dimensional depression. So in many cases the topographic highs which are created due to the very gentle folding of these rocks which are being deposited into these Epeiric seas will form island chains, and of course these island chains will get pushed above sea level where they can be eroded, and they'll obviously provide a source of sediment which is then deposited into the surrounding Epeiric sea. So in terms of modern Epeiric seas, there are several examples. In terms of North America, the most obvious example is the Hudson Bay. In terms of Europe, there's the North Sea and the Baltic Sea. In Southeast Asia, we have the Gulf of Thailand and the Java Sea are good examples as well. And you can see that all these bodies of water are sitting on top of these areas which are marked out in this kind of light minty blue colour. And this represents essentially continental crust that has seawater on top of it. Compare that to the much deeper ocean basins which are marked here in the dark blue, and in that instance the seawater is obviously sitting on top of oceanic crust. So during the Paleozoic we know there were 6 major continents. So there was Baltica, which consists of Western Russia and Northern Europe, so Scandinavia. There's China, which consists of a large part of China and some of mainland Southeast Asia. There's Gondwana, that consists of Africa, Antarctica, Australia, India, Madagascar, parts of the Middle East, Southern Europe and Florida. There's Kazakhstania, which consists of portions of Central Asia. There's Laurentia, which consists of North America, Greenland, Ireland and Scotland. And there's Siberia, which consists of parts of Russia east of the Urals, bits of northern Kazakhstan and Mongolia. And so these are the larger pieces of continental crust that are moving around on the surface of the Earth during the Paleozoic. Now there's also going to be smaller pieces of continental crust moving around, and these are referred to as microcontinents. And most of these microcontinents will typically get destroyed during the Paleozoic as they run in to the larger pieces of continental crust and they accrete onto the side. Now, most of the time we're just going to ignore the microcontinents, but there is one microcontinent that's important to us, and this microcontinent is called Avalonia. And Avalonia consists of Western Europe, Newfoundland and New England. And it's going to be important when we're thinking about the tectonic evolution of the eastern coast of North America. So let's think about the early Paleozoic for Laurentia. So the Phanerozoic sedimentary record for North America contains 6 cratonic sequences. So a cratonic sequence is what's called a large lithostratigraphic unit. So it's a big stack of rocks. And this big stack of rocks has essentially, will represent, should I say, a major transgressive regressive cycle. So they represent a big, thick sequence of rocks produced as the oceans transgress onto the land and then as the oceans retreat. And you can pick out these cratonic sequences in the rock record because the top and the bottom of them are marked by very large unconformities, which are normally craton wide. So they would normally stretch all the way from the east coast of modern day North America all the way over to the west coast. So the transgressive portions of these large lithostratigraphic units are often pretty well preserved, because obviously as new layers of sediment are being deposited, they naturally protect the layers of sediment below. And so during the first half, the transgressive portion of one of these events, obviously you're going to have lots of sediment being deposited, and so you're going to build up a nice thick stack of rocks. Now, during the regressive period, obviously, you're still going to have sediments being deposited and therefore rocks forming, but eventually, of course, the sea is going to retreat fully, and that's going to leave the rocks exposed, and they will therefore undergo erosion. So it's not uncommon for portions of the regressive part of the cratonic sequence to be lost, because, as I said, they were above sea level, they were open to erosion, and so rocks were destroyed. So where rocks of a similar age are preserved, the unconformities that mark the upper and lower boundaries of these cratonic sequences are observed to extend across all of, or at least over, large areas of North America. And when I'm talking about these 6 cratonic sequences, I am just talking about North America and the United States in particular. So this diagram here summarizes the events which are going on during the Phanerozoic. So to begin with, you can see this symbol here stands for the Cambrian, Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian, Permian, Triassic, Jurassic, Cretaceous, and then we have the Cenozoic. So these blue triangles are representing the orogenic events which are going to occur during this time period. The ones on the left represent events which occur on the modern day west coast, and the events on the right represent events which are occurring on the modern day east coast. And so what you can see is the width of the triangle here represents essentially the length of time. Obviously the broader the triangle, the more time the event took to occur. Typically also the height of the triangle here also represents the intensity of the event. So typically the bigger the event, the bigger the triangle will be. So if we look over here on the west coast, we're going to be discussing the Antler Orogeny as part of the Paleozoic. You'll notice though that's pretty much it for the Paleozoic on the west coast. Whilst over here on the east coast, we're going to be covering the Tectonic Orogeny, the Acadian Orogeny, the Achetan Orogeny, and the Alleghenian Orogeny. Now, the middle portion of the diagram here is actually covering what's happening with regard to sedimentation on the essentially the continent of Laurentia / North America. So this side of the diagram here represents the modern day west coast. This side of the diagram here represents the modern day east coast. So these brown areas here represent periods of time where the continent was exposed, so it was above sea level. So if we come all the way down to the bottom of the diagram here and we look at the start of the Cambrian, what we can see is that a large portion of Laurentia was above sea level, so it was exposed and therefore it was undergoing erosion. What you'll notice though is that the amount of rock that's exposed gets smaller and smaller and smaller as we progress through the Cambrian. This means therefore that the sea must be transgressing onto the continent, mustn't it? So we can see we have the sea transgresses from the west, the sea transgresses from the east, and the amount of exposed continental crust is getting smaller and smaller and smaller. And so this is one of these transgressive regressive cycles, and this first one is called the soak, or the souk. Then we have another period where we have a regression, the continent gets exposed again, and then we have another transgression, the continent starts getting covered over, and this is going to result in the formation of the Tippecanoe sequence. Then we have a regression, period of erosion again, then we have another transgression that's going to form the Kaskaskia, another period of erosion, then we have another transgression that's going to lead to the formation of the Absaroka sequence, another period of erosion, then we have the Zuni sequence being deposited, another period of erosion, then we have the Tejas sequence being deposited, and then finally, as you can see, steadily the seas have retreated until we're back to our modern coastline. So this represents the modern east coast of North America, and this represents the modern west coast of North America. So once we have our 6 cratonic sequences, we're obviously going to subdivide them into smaller units just because it's going to make them a little bit easier to work with. So these smaller units are very helpful to us. Obviously they'll allow us to correlate rocks at different locations, and they also allow us to undertake high resolution analysis of time and facies relationships in sedimentary rocks. So what I mean by that is, because we've studied these 6 sequences so comprehensively, it actually allows us to track how the facies related to the sequences are moving over North America as the Epeiric seas are transgressing and regressing. So this led to the development of a part of geology called sequence stratigraphy. And sequence stratigraphy is the study of rock relationships in a time stratigraphic framework of related facies bounded by erosional and non-depositional surfaces. So what that really means is it's the analysis of these 6 sequences and how they move backwards and forwards over North America with time. So the basic unit of sequence stratigraphy is a sequence, of which North America has 6. And of course these sequences consist of a package of rocks which are obviously bounded by an unconformity at the top and the bottom of the sequence. So these unconformities obviously represent periods of decreased sea level, so low sea levels, during which time the continents were exposed, open to erosion, so rock could be destroyed and thereby produce the unconformities. So the transition between the Permian and the Triassic is marked by the presence of the Absaroka sequence. So by the time we make it into the Triassic, the Absaroka is in full retreat, and we've already seen this diagram before. The Absaroka is going to start moving westwards, and as it's retreating, it obviously leaves behind isolated bodies of seawater which evaporate away to produce some localized sequences of evaporites. Now, the Epeiric Sea of the Absaroka sequence by the Triassic is pretty much limited to what is now North America's west coastal region, and we have erosion taking place across the centre and the eastern margins of North America. So the Absaroka Epeiric Sea obviously peaked in the Permian, and it was steadily regressing as we moved from the Permian into the Triassic, and most of the movement was either westwards or southwestwards towards New Mexico and Texas. So the Absaroka is obviously located right here, and we can begin to see as we move between the Permian and the Triassic, we can see the Absaroka is actually retreating already. And as we come across into the Triassic, there's actually another pulse. The Absaroka starts moving back inland, and then finally, as we are moving through the Triassic, we see the Absaroka is fully retreating, and we see North America is nearly fully exposed during the Jurassic. Now, as we essentially at that point, we're going to have another marine transgressive event, which is going to cover over North America, and this is going to give us the Zuni sequence. So in terms of the Absaroka Sea itself, as we've already discussed, the large amounts of sediment which were coming off the erosion of the central and eastern portions of Laurentia meant the Absaroka Epeiric Sea was dominated by detrital sediments, and of course this had the effect of inhibiting carbonate formation in a big way, because obviously in order to form large amounts of carbonates, one of the things you really need is nice clear water. And of course the problem we're having at this point is the water in the Absaroka Epeiric Sea would have been absolutely stuffed with fine suspended clays and silts in the seawater, so the water is going to be quite murky. So this obviously differs significantly from the earlier transgressive events which covered North America during the Paleozoic, because of course we know that these Epeiric seas were essentially clear, shallow and warm, and so they would have been perfect for carbonate formation. So we know the Sok, the Tippecanoe and the Kaskaskia, they were all carbonate dominated seas. In terms of the Absaroka, it was dominated by clastic sediments, mostly muds and sands. So what about the Zuni sequence? Well, the Zuni transgression begins in the Middle Jurassic and it extends all the way through into the Early Paleogene, so it goes through into the Cenozoic. Now, like the Absaroka, it was not a complete transgression. So if you remember, the Sok, the Tippecanoe and the Kaskaskia pretty much resulted in all of the United States being underwater and a substantial portion of Canada being underwater. In the case of the Absaroka, we had large portions of the United States and Canada above sea level, and obviously this meant we could create large quantities of clastic sediments through erosion. And the same thing is going to happen during the Zuni transgression, so it doesn't cover over all of North America or Canada, so there's plenty of rock to be eroded, so there's plenty of clastic sediment moving around. Now, this the amount of clastic sediment moving around at this point is very, very high because we have the formation of the Rocky Mountains starting. And obviously, as you know, any elevated terrain is going to naturally erode quite quickly, so the formation of a mountain range is going to lead to large amounts of erosion and obviously the production of substantial quantities of clastic material. So the Zuni sequence was driven by a transgressive event which was likely the result of mantle plume activity forcing spreading ridges upwards. So obviously we know that spreading ridges in the middle of the oceans, which we also refer to as divergent plate boundaries, actually are higher than the surrounding seafloor. They can be about 1 to 1.5 kilometers higher than the seafloor either side. Now, this is primarily because underneath the ridge we have large quantities of magma. And obviously magma is naturally buoyant, it wants to rise, and so the upwards force of this magma wanting to rise pushes the crust up. Now, what we think was happening in the Mesozoic is that these spreading ridges were becoming extremely active, which meant there was large quantities of magma trapped underneath the ridge. And by large, we mean huge quantities of magma. Now, this would have pushed the spreading ridges up even further. And obviously, as the spreading ridges get pushed up even more, they're going to displace seawater as they get pushed upwards. And obviously that seawater has to go somewhere, so it has to encroach onto the land. And that's obviously going to lead to a marine transgression. So the Epeiric Sea that's going to form is going to end up bisecting North America. So it's going to cut North America in two. So the formation of the Zuni sequence took place in two phases. So the first phase of the marine transgression produced what's called the Sundance Sea, and that was between the Middle to Late Jurassic. So the formation in the Sundance Sea was driven by a general global sea level rise, and obviously the ocean then moved onto the continents. Now, as we move into the late Jurassic, we begin to see the Sundance Sea retreating. Now, the retreat of the Sundance Sea is actually driven by the Nevadian orogeny. And what this does is it starts to push up the western side of North America. And obviously, as it pushes up the terrain, the Sundance Sea, which is sitting on the continental crust, obviously gets pushed back out into the ocean basin. Now, as we move into the early Cretaceous, we have the second stage of the transgressive event, which produces the Cretaceous Interior Seaway, also sometimes called the Western Interior Seaway. And this forms between the early Cretaceous and the early Paleogene. Now, this transgressive event is driven by the change in height of the spreading ridges. And now we've already discussed, this is due to the trapping of large amounts of magma underneath these spreading ridges. And they actually push the spreading ridges up so far that we think it might have led to an increase in sea level of about 250 meters. So that's a very substantial increase in sea level. Now, obviously, this very substantial sea level increase is going to lead to the seawater transgressing back over the continents, and so even though the western side of North America is being pushed up due to subduction, it's still not enough to stop the sea coming back onto the land, and that's going to lead to the formation of the Cretaceous Interior Seaway. Now, at the end of the Cretaceous, or the end of the Cretaceous going into the early Paleogene, should I say, the spreading ridges begin to subside, so the amount of magma trapped under the ridges begins to drop. And this, of course, means that the spreading ridges begin to decrease in height. That means essentially the seawater is now being allowed to move back into the ocean basins, and we see the Zuni transgression retreating. So at the end of the Sonoma Orogeny, subduction ceased and the western coast of North America became a passive margin. So if we look at the geologic timescale over here, we can see there's the Sonoma Orogeny straddling the Permian-Triassic boundary, and you can see that once the Sonoma Orogeny finishes, we have a period with little to no tectonic activity taking place. So the western coast has become a passive margin. Now, during the early Jurassic, we get subduction fully restarting along the west coast. And this leads to the formation of a steeply dipping subduction zone. Now, as we've discussed, the formation in the subduction zone is due to the westward movement of North America over the oceanic Farallon Plate. And of course, this is a direct reflection of the rifting that's taking place along the eastern side of North America, which eventually is going to lead to the formation of the Atlantic Basin. Now, the subduction zone that forms is going to control tectonism along the western side of North America from the early Jurassic all the way into the Cenozoic. So it's going to be active for a period of 140 million years. So it's a pretty long-lived orogenic event. And the start of subduction along the western coast of North America marks the beginning of the formation of the modern circum-Pacific orogenic system. So of course this is the ring of volcanically active mountain ranges that form along the edge of the modern day Pacific. So the Cordilleran Orogeny occurred between the Middle Jurassic and the Middle Paleogene, so it's a very extensive orogeny. Now, it consists of a series of individual mountain building events that occurred in different portions of the Cordilleran Mobile Belt at different times. So it's not that we're forming one big mountain range all the way along the western side of North America at one time. What we have are smaller mountain building events that lead to the uplift of the western side of North America at different times and in different locations. There is obviously going to be some degree of overlap though, because orogenic events are quite large, so you can have more than one orogenic event occurring in the same area at the same time. Now, as discussed, most of the tectonism that we see is related to North America's westward movement over the Farallon Plate. So the first stage is the Nevadian Orogeny, and this begins in the late Jurassic and it continues into the Cretaceous. So if we just go back to the previous slide, we can see, here we go, the Nevadian Orogeny is starting here in the middle to late Jurassic, and it's going to go through to the middle Cretaceous. So this then brings us on to the Sevier Orogeny. I should point out, by the way, the Sevier Orogeny, I've also heard it pronounced as the Sevier Orogeny or the Sevier Orogeny. So there are a few ways of pronouncing this one, but I believe the correct pronunciation is Sevier. So the Sevier Orogeny starts in the late Jurassic and goes through to the late Cretaceous. So it's following on after the Nevadian Orogeny, but it's also occurring at the same time as the Nevadian Orogeny, just to add a new layer of complexity. So it's the second stage of the Cordilleran Orogeny, and it affects North America from Alaska all the way down to Mexico. So this is a very extensive orogenic event. Now, as we just discussed, we know as we begin to transition from the Nevadian orogeny into the Sevier Orogeny, we have this shallowing of the angle of subduction. And this means that the stresses which were focused along the front edge of the subduction zone are now being spread throughout a larger volume of rock. And now this means that the subducting oceanic crust is going to spend more time grinding against the underside of the North American crust. And so this means we also have stresses being applied to areas of the crust that were previously unaffected by the earlier Nevadian orogeny. Now, the movement of these tectonic stresses inland is going to lead to substantial amounts of thrust faulting. So that's going to lead to sheets of rock being pushed up one on top of another. And of course, this is going to lead to the formation of a mountain range. So it's going to lead to the formation of topography. So this diagram kind of summarizes the basic situation. So at the top here we have the Nevadian orogeny. So we have our Farallon plate marked here as a thick black line, which is happily subducting underneath North America, and we have quite a steep subduction zone. So we can see that most of the interface between the two plates is going to be located right here, right at the front edge of the subduction zone. And so this is where most of the stresses are going to be located. And of course, we're going to have lots of mantle melting taking place here. So we end up building up a mountain range right here, right on the front edge of the continental crust. So this is the kind of situation we have in an area like the Andes, for instance. Now, what we see as we move into the Sevier Orogeny is we see the angle of subduction getting shallower. Now, as we've discussed, this means that volcanism begins to move eastward, so inland. But at the same time, it also means that we have a much greater area that's actively interacting with the subducting oceanic Farallon plate. And so this means the stresses, these tectonic stresses, are no longer being focused right at the front here. They're being spread out throughout a much larger volume of rock. And so this means that areas to the east of the Nevadian highlands are all of a sudden going to begin to experience compressive tectonic forces, and so this is going to lead to quite large amounts of thrust faulting, and this is going to lead to the formation of the Sevier highlands, essentially. Okay, so let's move on to the Laramide Orogeny. So we know the Laramide Orogeny is the final orogeny of the three orogenies that formed the larger Cordilleran mobile belt. Now, the Laramide Orogeny began in the late Cretaceous, so we already discussed it a little bit from the previous Earth history lecture. However, it continues going until the Middle Paleogene, to be more accurate, the Eocene. Now, the orogeny was not focused in a region proximal to the trench, and this differs significantly from the Nevadian and the Sevier orogeny. So the Nevadian and the Sevier orogenies were essentially focused more towards the trench itself, so more towards the subduction zone. And this is because a lot of the pressure, a lot of the force from the subduction event was being focused at the contact between the two pieces of crust, essentially the oceanic crust of the Farallon plate and the continental crust of the North American plate. And because they were pushing against each other right at the point of the subduction zone, that meant most of the pressure was located quite close to the trench. And so we tend to find the Nevadian orogeny especially has most of its deformation very close to the trench. We know the Sevier orogeny, most of the deformation was slightly more to the east, and by the time we move into the Laramide orogeny, we can see that the deformation has moved even further east, so it's gone even further inland. Now, we've already touched on the fact that this change in the position of the deformation is the result of a change in the angle of subduction of the Farallon plate underneath the North American plate. So unlike the Nevadian and the Sevier orogenies, which mostly consisted of quite strong compressional tectonics, which resulted in quite tight folding and lots of thrusting, the Laramide orogeny actually produces a different style of deformation. So with the Laramide orogeny, we see quite a lot of vertically uplifted fault-bound blocks. So we get these big blocks of rocks being pushed up on using steep reverse faults. Now, most of these steep reverse faults are probably actually pre-existing normal faults that have just been reactivated. So the fault is already there, and so all tectonism has to do is just simply use it again, because it's the easiest way of doing things. Now, once again, the Nevadian and the Sevier Orogenies were associated with volcanism. The Laramide Orogeny is not. So we don't really see much in the way of volcanic activity during the Laramide Orogeny. We also see that in terms of deformation, we lose the tight folding that we get with the Nevadian and Sevier Orogenies, and instead the folding we get with the Laramide Orogeny is more open, gentle, so you get these quite broad folds. And of course, as we've already touched on, the region which is being deformed as part of the Laramide Orogeny has moved even further to the east. So essentially, we've been progressing from the Nevadian Orogeny, which was located quite close to the modern day west coast of North America. Then as we step east, we then had the Sevier Orogeny, and then as we move even further east, we then move into the terrain which is being deformed by the Laramide Orogeny. So to account for this eastward shift, we have to make adjustments to the subduction model for the mountain belt. So during the Nevadian and the Sevier Orogenies, the angle of subduction of the Farallon plate is somewhere between about 50 and 20 degrees. So we know subduction initially started off being quite steep during the Nevadian Orogeny, and then as we move from the Nevadian into the Sevier Orogenies, we begin to see the angle of subduction shallowing. So the subduction produced plutonism and volcanism between 150 and 200 kilometers inland. So if you remember, the subducting oceanic crust will go down into the mantle until it reaches a depth of approximately 150 kilometers. This is the point where the mantle the oceanic crust, will dewater. That water goes into the overlying mantle, and essentially it melts it through hydration melting. So the mantle melts, producing a mafic magma. That mafic magma rises straight up, gets stuck at the base of the continental crust. It partially melts the continental crust, producing felsic and intermediate magmas, and those felsic and intermediate magmas rise through the continental crust and essentially are erupted onto the surface via volcanoes. Now, the vast majority of this volcanic activity is 150 to 200 kilometers inland from the trench which is running parallel to the west coast of North America. And so this tells us that essentially the subducting oceanic crust was making it down to that magic 150 kilometer depth, approximately 150 to 200 kilometers east of what is now the modern day west coast of North America. So combined with this volcanism, we see a lot of essentially compressional tectonics resulting in tight folding and lots of thrust faults. And so this is what we expect to see in a normal convergent plate boundary. Now, by the late Cretaceous to early Paleogene, it's thought that the angle of subduction had shallowed to nearly horizontal. And so this means that instead of diving down into the mantle, the subducting piece of Farallon plate is actually just grinding along the bottom of the North American plate. So of course, number one, this means the subducting Farallon plate is never going to make it down to that magic 150 kilometer depth, and so you don't get any melting, so obviously you're not producing magma, so that means no volcanoes. It also means that the area which is being deformed by the interaction between these two pieces of crust is now considerably larger, because rather than all the pressure being focused towards the subduction zone, it's now spread out along the entire bottom of the western side of the North American plate. So this means that the tectonic forces are a bit more dispersed, so we lose the very, very tight folding, and we lose the thrust faulting that we've seen with the Nevadian and the Sevier Orogenies, and it's replaced with very broad open folds, which tells us the pressure is a little bit lower, and the reuse of pre-existing normal faults, producing quite steep angled reverse faults that push blocks of rock straight up. Now, the question becomes, why did the Farallon plate change its angle of subduction? So there's a couple of possible reasons which might explain why the Farallon Plate essentially found it so difficult to subduct. The first possible reason is that attached to the Farallon Plate there was a buoyant oceanic plateau. Now, most oceanic plateaus on the seafloor are the result of flood basalt eruption. So that's when you have a large fissure eruption on the seafloor, so huge amounts of basalt come pouring out onto the seafloor, and essentially it creates an area of raised terrain on the seafloor. And of course, as the name suggests, this area of raised terrain has a flat top, so we call it a plateau. Now, some ocean plateaus, on the other hand, can actually consist of continental crust, and as we know, continental crust is actually quite difficult to subduct. So if we have a very, very thick ocean plateau made of basalt, or some kind of oceanic plateau that's made of continental crust, well, when that oceanic plateau is being subducted, because remember it's sitting on top of the Farallon Plate, it's going to be naturally buoyant, so it's going to naturally want to rise. Now, this is a bit of a problem because the Farallon Plate wants to go down into the mantle. It wants to essentially wants to subduct, but this buoyant oceanic plateau is going to counteract that. So it's going to want to pull the subducting slab upwards. And so if you had a large enough oceanic plateau that was buoyant enough, it would be sufficient to pull the Farallon Plate essentially into a shallower angle of subduction, and eventually leading it to subduct almost horizontally along the underside of the North American plate. So that's option number one. Our second option is that there is a mantle plume that gets stuck underneath the Farallon Plate. So obviously to the west of the Farallon Plate we have the Farallon Spreading Ridge, which is where new oceanic crust is being made. Now, a lot of the time when we have oceanic ridges, it's not uncommon for mantle plumes to get trapped under the spreading ridge. And this is because most spreading ridges are located at the interface between convection cells in the mantle. So you have two convection cells that are running parallel to each other, and the contact between the two of them is a very, very common location for spreading ridges to form, but it's also a good path along which rising mantle plumes will move. It's a path of least resistance. And so it's not uncommon for mantle plumes to get stuck underneath spreading ridges. The classic example of that is, of course, the mantle plume that's forming Iceland, which is a big mantle plume that's currently trapped under the Mid-Atlantic ridge in the North Atlantic. Now, in the case of the Farallon Spreading Ridge, we think there's a chance that the mantle plume might have been moving up to essentially rise underneath the Farallon Spreading Ridge. However, instead of going straight up and getting caught under the ridge, it in fact got deflected and it went to the east, and it got trapped under the oceanic crust of the Farallon Plate. And so what this means is underneath the Farallon Plate, you're going to have this big ball of very hot, very buoyant mafic magma. And so once again, this is going to have the effect of pushing up the Farallon Plate, thereby making it far more difficult to subduct. And so obviously, because you've got this big buoyant mass of magma trapped underneath it, when it starts to try and subduct that piece of oceanic crust with the magma underneath it, it's not going to subduct easily. In fact, the magma is going to be so buoyant, it's just going to push up the Farallon Plate, and once again it's going to make the angle of subduction become near horizontal. Now, out of these two models, the mantle plume model is the preferred option. Now, obviously, as we've said, the shift in the angle of subduction leads to volcanism ceasing, because obviously if our piece of subducting oceanic crust is not making it down to 150 kilometers, it's not melting the mantle, so we're not producing magma. So finally, we're just going to drop back onto the Gulf Coast region. So following the regression of the Zuni Epeiric Sea at the end of the Cretaceous, there was a final marine transgression that occurred in the late Paleocene and Eocene epochs. So this is the Tejas Epeiric Sea, and this particular Epeiric Sea was, compared to the others at least, tiny. So it was a relatively small Epeiric Sea, and it was pretty brief. It wasn't around for very long. At its maximum extent, it was restricted to the Atlantic and Gulf coastal plains, although it did also encroach on some areas of California, not many. The furthest it managed to move inland was the area which is now marked out by the Mississippi, Arkansas, Tennessee junction. So you can see here it is. So you can see we have the Atlantic plain here, Florida here, and the Gulf Coast plain here, which are inundated. We can see that this area here represents the maximum extent of the Epeiric Sea, reaching this Mississippi, Arkansas, Texas junction right here. So you can see it wasn't a particularly extensive body of water. So the sedimentation pattern for the Gulf Coast was established in the Cretaceous and continues until the present day. Essentially, it's an area which is dominated by continental marine sediments. So the sediments that are eroded from the eastern Laramides, western Appalachians essentially are transported across the Great Plains and central lowlands, and they're deposited in continental, transitional and marine environments, depending on where the rivers drop them. So this deposition once again produces one of these seaward thickening wedges. So if we look at the sedimentary sequences associated with the Gulf Coast, once again we have a triangular shaped body of sediment. It's thinnest closest to the coast, and it gets thicker as you move out into the marine environment. And once again, this is a standard passive continental feature. We tend to see a lot of these seaward thickening sedimentary sequences associated with passive continental margins. So the sedimentary facies development that we see in these wedges of marine sediments that were being deposited from the Cretaceous onwards are controlled by the regression of the Tejas-Epeiric Sea. So as part of this Epeiric event, we actually have 8 minor transgressive regressive cycles, which we can see in the sedimentary sequence. And so this means obviously the facies are going to be shifting depending on whether the ocean is transgressing or regressing. And so this means the sediments associated with the Tejas sequence essentially show quite strong intertonguing as the facies were moving due to sea level changes.